All right, so the focus of the second hour this morning is, again, we're going to start with a little bit of review, and then we'll get into some application and some stuff that I'm sure you're aware of, but we haven't done a whole lot of calculation work with yet. And that is pH concentrations and starting to use some of that hydronium hydroxide information from autoionization to answer some questions. So let's start with acid and base strength. So this is review for you. This is stuff that we covered in Chem 105. We know that strong acids are strong electrolytes, that breaking apart of the molecule is a full break. There is no equilibrium to it. It is a complete break from one side to the other. Now, on Monday, we'll talk about acid strength from a standpoint of equilibrium constant. And what we'll see is that even strong acids have equilibrium constants. However, those equilibrium constants are in like the 10 to the 8th, 10 to the 9th kind of range. And once we get past like 10, we start to think of acids as strong, and their dissociations as relatively complete. But you know, they're the 7 strong acids on the board there. Those are ones that we all saw last semester, Chem 105. Your halo acids, the binary acids, hydrochloric, hydrobromic, hydroiodic, the oxo acids, nitric, sulfuric, chloric, and perchloric. And so again, the idea here is strong acid, strong electrolyte, complete dissociation. When these react with water, we don't put the double-headed arrow on them. We largely consider them to be one-way reactions. Strong bases, again, same kind of thing. When these things dissolve in water, the hydroxide cleaves completely from the cation and goes and reacts with the water. Goes and reacts. So where do we find those? That's group 1 and group 2, basically. And again, because their dissociation is considered complete, and because their reactions are considered one way and not reversible, we consider those strong electrolytes. These are the kinds of things that in a net ionic equation, we break apart completely. So this information is not new to you. This is exactly the kind of stuff that we talked about in Gen Chem 1. It's the same kind of stuff that we would expect to know, right out of the gate here in Chem 2. At the molecular level, one difference that we can start to talk about now that we have a better understanding of what the solvent dynamic is, and how acids work from that Bronsted-Lewis kind of perspective, we can see that when this breaks apart, HCl turns into H plus and Cl minus. And it's that H plus that is going to go to the water to make hydronium and chloride ions. And at the molecular level, that's exactly what we would see. Is now, mind you, all of these ions are surrounded by water molecules. We're leaving them out just so that it's easier to see. But inside of that hydrochloric acid solution, all that we see in that solution, other than water molecules, are chloride ions and hydronium ions. But in a weak acid, notice a couple of key differences. One, the reaction is not drawn in as one way. It's drawn in as reversible at equilibrium. And as a result of this equilibrium, we are going to see a combination of all three of the reacting species in this equilibrium. Again, omitting water here. So we know that the hydrogen is going to come over and make hydronium. But since that equilibrium is so reactant favored, what that means is that the majority of the equilibrium lies on that reactant side of the ledger. And what do we see? Well, we see in this instance that here's an unreacted molecule, here's an unreacted molecule, here's an unreacted molecule. We've got all of these unreacted molecules of HF, and only a couple of them have actually broken down into hydronium and fluoride. The majority of the hydrogen fluoride molecules have stayed as hydrogen fluoride. Only a couple of them have broken down into ions and formed those acid-base reactions. And that is the biggest difference between the strong acid and the weak acid. The reversibility of the step, meaning that we have equilibrium, and the fact that the equilibrium is so reactant driven that it is very reactant heavy inside of that solution. So we talk about weak acids in terms of their inability to dissociate completely. We talk about them in terms of their equilibrium. And so we know that there are ions in that solution. We can see it in the diagram that we just made. There are ions in this solution. So this solution will conduct electricity based on those ions being present, but it's going to do so in a much weaker fashion. So as far as weak acids go, we tend to focus on a couple of really common examples. So on the inorganic side, we talk about hydrofluoric acid, we talk about phosphoric acid. Hydrofluoric acid is actually particularly nasty stuff. If you happen to encounter hydrofluoric acid in any kind of considerable concentration by accident, it actually can really wreak havoc on your body system because it can react with the bones in the calcium in your bones and calcify it. It's a mess. Nasty stuff, even though it is a weak acid. Phosphoric acid, you actually find very commonly beverages such as sodas, colas, tend to use phosphoric acid as a pH stabilizer. The most common organic weak acids, the carboxylic acids, where we tend to see these. So this is formic acid. We saw it in an earlier example. This is what is actually secreted by ants. So if you ever get an ant sting, the reason it stings is because their venom, so to speak, is formic acid. And so when they bite you, formic acid gets into the wound and it hurts. Lactic acid, that is a byproduct of metabolism. If you go through and do a lot of anaerobic activity, lactic acid will build up in your muscles. That's one of the things that makes your muscles feel achy and fatigued during exercise. Probably the most common one that we know, acetic acid. That is what is in vinegar. Vinegar is roughly 5% solution of acetic acid in water. So that classic smell that you get is actually from the acetic acid and also the tartness. Um, Now, the difference between white vinegar and apple cider vinegar and other kinds is mainly the source material. Vinegar is a common byproduct of fermentation. If you let fermentation go on for too long, the alcohol that you sought initially actually turns into vinegar, which is what happens when wine goes bad, basically. If you've ever noticed that, and some of you might be too young to know this legally, but wine, if you open up a bottle of wine and it sits for a period of several days or a week, if you go to drink it out of the bottle after a significant period of time, it can taste sour. One of the reasons it tastes sour is once you've opened the bottle up to oxidation, the processes of turning the alcohol into vinegar accelerate under the fact that you've introduced oxygen into the bottle. Carbonic acid is found in mammalian blood, including your own blood. This is a product that is actually regulated in your blood for pH purposes. And more on that in a little bit. Just like with weak acids, weak bases do not dissociate either. They are in reversible reactions that generate weak electrolytes. And again, the key attribute that we would look at in the chemical equation itself is the fact that we've got this reversible arrow here. The equilibrium arrow tells us that we're dealing with a weak base instead of a strong base. So as far as weak bases go, other than ammonia, which is kind of the classical example of a weak base, most weak bases are nitrogenous, nitrogen-containing organic molecules. And probably the most well-known class of those molecules are the alkaloids. All of the alkaloids are weak bases in their own right, and they're weak bases on the basis of this nitrogen. Again, thinking about nitrogen in that Lewis kind of definition, where I've got this lone pair of electrons on the nitrogen. And depending upon the environment, that lone pair of electrons can go out and grab something else, whether it's a hydrogen, whether it's another molecule, and that is the basic behavior that we're talking about. So when these molecules find their way into water, that's how they proceed to become basic in their activity and basic in their pHs, some more so than others. Another common class of organics are the amines. These are organic derivatives of ammonia. And these ones are actually commonly found in the body, where we've got adrenaline. This is your fight or flight response produced by your adrenal glands. Serotonin and dopamine, these are found in your brain. And what we see in all of these cases is that you've got a nitrogen that is near the end of a carbon chain, and it can go out and again, if we put adrenaline into water, that lone pair will grab a hydrogen off of the water. If we put it into other kinds of circumstances, that lone pair on the nitrogen could react similarly and form new bonds. So our last topic for this morning and this week concerns we're able to identify acids and bases now, and we can do it in a variety of ways. We also, because of Lewis theory, can still take a decent idea and look at a chemical structure, maybe not necessarily a chemical formula, but a chemical structure and say, okay, this molecule looks like it's probably geared toward acidic behavior. This one's probably more geared toward basic behavior, at least based off of that. But the last thing that we want to get into is quantifying how acidic or basic a solution is. And for that, we need the pH scale. Now, we all probably have at least some rational understanding of the functionality of the pH scale. We've heard of it. We know that the pH scale gives us an indication of acidity or basicity. We know that neutral pH is 7. We probably also know that pH is below 7 are acidic, pH is above 7 are basic. But we may not necessarily have a whole lot of understanding about how we came to those numbers. And that's what we're going to get into today. So pH, P standing for power, H for hydrogen, or more specifically, hydronium. We can calculate the pH value of our solution by taking the opposite of the log of the concentration of hydronium ion in that solution at equilibrium. And similarly speaking, we can reverse the process. If we needed to calculate the amount of hydronium in the solution, we could do so by taking the antilog of the pH. So 10 to the negative pH value would give you that hydronium concentration at equilibrium. Now, the other half of the scale, the other half of this slide, concerns POH. POH is basically the mirror image of pH. Instead of focusing on hydronium, it focuses on the other product of autoionization, the hydroxide. But the calculations involving POH and hydroxide are essentially the same. POH is equal to the opposite of the log of hydroxide concentration at equilibrium. And if I wanted to find the hydroxide concentration, I could take the antilog of the negative POH, 10 to the negative POH. What ties these two together is that pH and POH equal out to 14 when added together. Now, I'm going to add just a small caveat to this. This is true if we are working at essentially room temperature 25 degrees Celsius. Now, as we saw in the previous chapter, the value of an equilibrium constant will change with temperature. So we have to understand that the calculations that these are based off of are value of Kw, 1 times 10 to the negative 14th. Those are all tied to temperature being 25 Celsius, or at least close to 25 Celsius. If we change the conditions up or down, well, we would expect, based off of the Van Hoff equation, that our equilibrium constant would change as well. But for the most part, we're going to stick to this primarily because majority of acid-base work that we do is going to be at room temperature. And even if our room temperature isn't exactly 25 degrees Celsius, it's usually close enough that we don't need to care. So if we're doing work up in the lab, I think our lab has been right around 21, 22 degrees Celsius, at least for the water temperature, maybe not the air temperature up there. But if that has been the case, it's close enough that we're just going to kind of round to the margins there. But if we start doing experiments at like 70 degrees Celsius, for whatever reason you might do those. Well, in that circumstance, none of these would apply exactly. We would have to figure out what KW is at 70 and make adjustments from there. So just some general kinds of ideas here. If we're at 25 degrees Celsius, the typical range for the pH scale is 0 to 14. 0 would be extremely acidic. We're talking about things like 1 molar hydrochloric acid or greater. We're talking about things like battery acid that you would find in your car. That battery acid is sulfuric acid. At pH 14, we're talking about things like liquid plumber and Drano, which are usually a mixture of sodium hydroxide and bleach. And what they do is they take care, the way that those work is they take on hair and grease and other things that usually clog your drain are usually quite reactive toward bases. So what they do is they dissolve the gunk, and that's what clears the drains. So the question is, how do we get to here? Well, we got to go back to our original talking point when we looked at autoionization. So we were told that at 25 degrees Celsius, our equilibrium constant for the autoionization of water is 1 times 10 to the negative 14th. And if we solved out the ice table there, we would have 1 portion of hydronium, 1 portion of hydroxide, or x squared. The hydronium concentration would be equal to x, which would be equal to the square root of 1 times 10 to the negative 14th, which would be 1 times 10 to the negative 7th. I plug that into my pH calculation. So 1 times 10 to the negative 7th, logarithm of that, opposite, I get a pH of 7. Since pH and pOH have to equal 14, if the pH is 7, then the pOH must also be 7. So this is how we come up with the number there for pH 7 as being neutral. Because when the two concentrations are equal, they're both equal to 1 times 10 to the negative 7th molar, and the opposite of the log of that is 7. So let me introduce you to something called the calculation box. When it comes to describing acid-base solutions, there are generally 4 things that we can use to describe any solution. We can describe a solution in terms of its pH, its pOH, its hydronium concentration, and its hydroxide concentration. And what this box does is it allows us to show how we can interconvert between any one of those calculations and the other. So for example, if I know the hydronium concentration and I want to figure out the hydroxide concentration, I can use the Kw equilibrium expression to figure out the difference, to figure out whatever's missing. If I want to go between hydronium and pH, well, if I have pH, I would use the antilog. If I have hydronium, I would use the pH equation to figure out how to get pH from that hydronium concentration. What this also shows us is what if I wanted to go across the diagonal in any of these directions? Well, what it shows us is that there is no direct calculation between hydronium and pOH. So I can't go directly across the box. But there are two pathways that I can go to get from hydronium to pOH. I could turn the hydronium into pH and then the pH into pOH. Or I could turn the hydronium into hydroxide and then the hydroxide into pOH. So to go across the diamond, I've got to go through two calculations. But otherwise, I can convert between any one of these and the other with a relatively simple calculation. And all of these equations, in one form or another, are present on the equation sheet for this chapter. Now, they're not all exactly in this form. I believe the equation sheet says Px is equal to the negative log of x because, well, the P represents a function. The function is logarithm. But looking ahead to the homework over the weekend here, a lot of what's in assignment 14-1 is this acid-base definition stuff. But the stuff at the end are these interconversion calculations. And so let's do a couple of examples of those before we break for the week. Before we do, let's just talk a little bit about measurement. So you are familiar already with these two methods of measuring pH. Litmus paper, pH test strips. If you have a pool or a hot tub at your house, this is the same kind of stuff that is on those test strips that you would dip into the pool to get after things like alkalinity or chlorine concentration or anything like that. Litmus is a great qualitative test of acidity. It basically gives you is this acidic or is this basic kind of idea. It doesn't really give you any kind of, this is pH 2 or this is pH 5 or this is pH 12 kind of information. pH meters are by far the more precise and accurate way to measure pH. And when times are appropriate, they are exactly what we would use in the laboratory situation as well. But most of the time, we usually rely on these kinds of less quantitative, more qualitative methods, because we really just don't need that kind of major information. When we think about some of the things that we've done in lab thus far, basically we've only cared about, is it acidic or is it basic? Because if it's basic, that's actually what we want to see the reaction that we're looking for. It doesn't matter to us that it's pH 12 versus pH 10. All that it matters is that it's a basic pH. when we get into some more detailed kinds of things, especially with the next chapter, pH meter is going to come into our conversation then as well. All right. Guided practice problem. As your food's being digested, it leaves your stomach, which has a pH of about 4.5, to your small intestine, where the pH is about 7.5. What we want to do is convert the pH of 7.5 to POH, to hydronium, and to hydroxide concentrations. So the way to tackle this is, if I'm looking at the calculation box here, I have been given the pH. Now, since I have to calculate all of the other ones anyway, I'm going to have to go around the box in some kind of way or another. Now, let me tell you my own personal preference, and then you can kind of decide for yourselves. Personally, I find the calculations that deal with logarithms and with subtraction far easier than dealing with the equilibrium. And the only reason I say that is mainly because these equilibria are going to involve multiplication and division, where I have to use scientific notation. Because almost always we're going to end up with hydroxide or hydronium concentrations where I've got some kind of scientific notation concentration. Something times 10 to the negative fifth, something times 10 to the negative 12th, something times 10 to the negative eighth. And in those situations, it's far easier to make a mistake with your calculator, especially if you're not good at using the scientific notation button on your calculator. Where instead of getting something times 10 to the negative first, your calculator blended together the exponents and gives you a 10 to the negative 11th instead. Or you get a concentration of 5 billion, and you go, how on earth is that possible? So for me, I try to avoid this bottom conversion as much as possible, just because it is the easiest one to make mistakes with. Now, that's my personal preference. And so what you'll see me do is, in this problem, I will go from pH to hydronium this way. I'll go from pH to POH this way. And to find the hydroxide concentration, I'm going to go from POH to hydroxide using anti-log. That's going to be my preference. That's how I would approach it. Now, you can kind of work out the details for yourself. You're going to have some practice problems over the weekend in that homework assignment. You can kind of figure out your own style. But that's where I sit on this. So for pH 7.5, first thing I would want to do is turn that into POH. So since 14 is equal to the pH plus the POH, I subtract 7.5 from each side. I get 6.5 for the POH. Right. Have to be mindful of your significant figures. Have to be mindful of the significant figures. Since I'm only given one decimal place for this pH reading, I can only have one decimal place in the POH as well. All right, I'm going to take the POH and turn it into hydroxide. Hydroxide concentration is equal to 10 to the negative POH. We just found that the POH was 6.5. So anti-log of negative 6.5. Okay, my calculator tells me 3.16 and change times 10 to the negative 7th. We haven't had to deal with this yet. How do I handle logarithms and sig figs? And the answer is this. The rule of thumb is that the number of sig figs in the concentration becomes the number of decimal places coming out of the logarithm. So the POH or pH decimal places are the number of sig figs in the concentration. So since I only have one decimal place here, I would only have one sig fig in the concentration. So decimal places turn into sig figs. So this is going to be 3 times 10 to the negative 7th for molar. Now for hydronium, I'm going to start with the pH. So concentration of hydronium is equal to the anti-log of the negative pH. So 10 to the negative 7.5. And same kind of deal applies here. One decimal place means one sig fig. I'm going to have 3 times 10 to the negative 8th molar hydronium. So this is the way I would approach this problem. Now, there's one other calculation that you could have done. You could have gone from hydronium or from hydroxide to hydronium using KW. Had you done that, it would have been 1 times 10 to the negative 14th divided by 3 times 10 to the negative 7th. And again, one sig fig, you would have got the same answer, 3 times 10 to the negative 8th. So as I was saying, that is a personal preference thing. Yeah, the other two calculations, the middle calculations, you could have handled either direction. Yeah, you could have gone a number of different ways to get those. But for the hydronium concentration, I find that anti-log is a little bit easier to use. Just because I don't have to throw in a whole bunch of exponents. I just have to remember that sig fig rule. And with that sig fig rule, once you get used to using it, it becomes like any other sig fig rule. It's just something that kind of becomes a part of your everyday use. All right, any questions with that? All right, final example for the week. This one is a little bit more straightforward. Calculate hydroxide concentration if you have a pH of 2.67. So you should notice right away, this is one of those across the diamond kind of calculations. So you are going to have to do two separate calculations to get to hydroxide, but how you choose to do it is completely up to you. All right, looking around, we're we're all basically on the right track. Let's just make sure that we've got the sig figs tied down. So the way I would go about it is knowing that we have pH, I would take it to the pOH and then to the hydroxide concentration. So pH is 2.67. To turn it into pOH, I would need to subtract from 14. So that would be 11.33. And again, we keep 2 decimal points there because our original calculation or our measurement had 2 decimal places as well. We can consider that 14 to be exact. So really it becomes a matter of input in, input out. So whatever number of decimal places go into that subtraction, that's the number that need to come out as well. To turn it into hydroxide, 10 to the negative pOH is the result. So 10 to the negative 11.33. If I do that calculation, 2 decimal places means 2 sig figs. So 4.7 times 10 to the negative 12th molar would be the correct answer for this question. And, walking around, that's pretty much where everybody was, save for a little bit of rounding here and there. All right, so that's where we're going to stop for today and for this week. So go ahead and get that last participation point. When we come back after the weekend, we're going to start looking much more closely at the equilibria of those acids and bases and starting to quantify those relationships using equilibrium constants. And we're going to come back to ice tables because that's going to be a central feature of those calculations. So that's all for this one, and we'll stop.